2.4 is scatterplots, correlation, and regression. You maybe will remember linear regression from a previous class. It's kind of the same thing, but we're going to get more involved and more in detail with what some of the numbers represent. Key concepts. Introduce the analysis of paired sample data. When they talk about pairs, they're basically talking about like XY points, numbers that go together. They don't have to be an X and a Y, but it's numbers that go together, pairs of numbers. Discuss correlation and the role of a graph called a scatterplot. Provide an introduction to use of linear correlation coefficient. And provide a brief discussion of linear regression, which involves the equation and graph of the straight line that best fits the sample paired data. So a scatterplot, you're going to have a bunch of dots. And you're trying to draw a line that best represents those dots. Line of regression through the scatter plot, that's kind of what we're trying to do. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. One way to think of it is, as this increases, this other thing also increases. That would be a positive correlation. As one of them increases, the other one increases. Doesn't mean that one of them caused the other, but as one increases, the other one increases. Okay. As the temperature rises, the ice cream truck sales also increase. Those two variables, the temperature and the ice cream truck sales, okay, those two variables have a correlation, a positive correlation. Linear correlation exists between two variables when there's a correlation and the plotted points of the paired data result in a pattern that can be approximated by a straight line. That's a lot of words to just say it's a line. All right, linear correlation, there's a line through, as opposed to a parabola or some other shape. Scatter plot is a plot of paired XY quantitative data. There's that word again. Quantitative means numbers, right? With a horizontal x-axis and a vertical y-axis. The horizontal axis is used for the first variable, and the vertical axis is used for the second variable. All right, so you see an example here with the scatter plot. Discuss whether a correlation between the variables seems to exist. If so, what does that mean in the situation? So basically, you're just kind of looking at the pattern. All right. So I mean, it seems to be increasing, right? It seems to be going uphill, right? I mean, if I tried to draw a line through, you know, that line's a decent representation of the dots. I'm not going to hit them all, but it sure seems to be, okay? It seems to have a positive correlation. Now, why I've accented the word seems is we're going to get into some of the numbers later, and we'll be able to prove if it actually does or whatever, but it sure looks like it has a positive correlation right now, and we're talking about slope, essentially. What does that mean? Well, we're talking about waist circumference and arm circumference. So what that means is as waist circumference increases, arm circumference increases. Okay. I guess the bigger you are around the belly, the bigger your arms are, is what that appears to say. Number 2, weight and pulse rate correlation. Discuss whether a correlation between the variables seems to exist. If so, what does that mean in the situation? Well, it's a lot harder to draw a line and to predict what's happening here. Okay, I can't really tell if there's a correlation or not. You know, you try to draw a line, I'm not really sure if that's going to happen. All right, I'm not really sure if that's a good representation. Is that better than this? I'm not really sure. Okay, I'm not really sure. You know, who knows really? It's very difficult to tell here. Another way of thinking about that is if I made a new point, and I wanted to do some kind of point out here at 175, you don't know if that dot's going to be up here or down here. You can't really tell, because you can't really tell if this thing is increasing or decreasing or what. So I can't really tell. No correlation seems to exist. So since we're talking about weight and pulse rate, we would say something like, as weight increases, you can't really tell if pulse rate increases. Can't really tell. Linear correlation coefficient R. This is kind of an important concept. The linear correlation coefficient is denoted by R, and it measures the strength of the linear association between the two variables. It's a number that tells us how good of a correlation it is, how strong of a correlation it is. In other words, it tells us how well the scatter plot fits a straight line pattern. How well the dots fit a straight line pattern. Using R for determining correlation, the value of the linear correlation coefficient R is between -1 and 1. I believe we did that a little bit last semester in finite. We're going to dig more into it a little bit though. If R is close to -1 or close to 1, there appears to be a correlation. If R is close to 0, there does not appear to be a correlation. So that's kind of saying we're looking for an R number that's close to 1 or close to -1. If the closer it is to 1 or -1, the closer it is to a perfect line. If it was exactly 1, we would have a perfect line. All right. Also, this negative is talking about a negative slope, and a positive number is talking about a positive slope. So that's just kind of something subtle. 0, we wouldn't be able to tell, I guess, if it was positive or negative. Next is this concept of p-value. And this was new to me, so you'll want to listen very carefully here. This will be new to you, I think, as well. If there really is no linear correlation between two variables, the p-value is the probability of getting paired sample data with a linear correlation coefficient R that is at least as extreme as the one obtained from the paired sample data. Might want to read that again. Okay. We can interpret a p-value. It says only a small p-value such as 0.05 or less, that's important, or 5% chance or less, suggests that the sample results are not likely to occur by chance when there's no linear correlation. So a small p-value supports a conclusion that there is a linear correlation between the two variables. All right, this is what we want. We want this p-value to be less than or equal 0.05. That's saying it's not likely to happen by chance. It's not likely to happen by chance. If I look at this next graph, if you're trying to draw a line through those 5 dots, it's kind of hard to tell how to draw a line through. It looks like maybe there's a positive correlation. I don't know, maybe. It's kind of tough. kind of tough to tell, but there's only 5 dots there, and I could randomly throw 5 dots down, and it might look like a positive correlation. All right, so is it possible that I randomly put 5 dots and it shows me a positive correlation? Well, this p number is going to tell me if it could be random or if it could have happened by random chance or not. If that p-value is less than 5%, it wasn't random. It's not a coincidence, and that tells me that there's a linear correlation. So you've got this table of shoe print length and height. It's talking about the length of somebody's foot compared to their height. Does there appear to be a strong correlation between the two variables? Well, doesn't appear to be. Doesn't appear to be a strong correlation, and that's kind of just intuition. You're kind of looking at it, and it doesn't feel like a tight pack of dots. A tight pack of dots, form a straight line, a perfect straight line. That's not very tight. Doesn't appear to be a strong correlation. So it says use a regression calculator to find the correlation coefficient. What does this tell us? All right. So I'm gonna go to my regression calculator here. This gray link right here, linear regression, and I'm gonna have to type in those numbers. So give me a second to type them in. Okay. So I just did a linear regression on those 5 dots, and there's kind of what the line through those 5 dots would look like. And we scroll down and we can see all these numbers. And these numbers hopefully will tell us some things. When you've used this in the past, all you did was go down to the bottom. The bottom line gives you an equation in slope-intercept form, and that's useful. But what we want is we want to find the correlation coefficient, which is R. Now, they don't give us R. The best thing they give us is R squared. If you look right here in the middle, R squared is this 0.3496 number. And so we have to do a little bit of figuring. That's not what I want. R squared is 0.3496. All right. That is not the correlation coefficient. We want R, not R squared. And so what we need to do is take the square root of both sides. So we need to solve this for R. So we're going to take the square root of both sides. But what's weird is, and what you can't forget is an equation like this has 2 solutions, the plus or minus root. Okay. So we would take the plus or minus square root of 0.3496. So square root of 0.3496 is 0.5913, I guess, right? 0.5913. But here's the thing. I know that equation has 2 solutions, but we can tell which one to choose because we can tell this line goes uphill, all right? If that line goes uphill, it appears that there is a positive correlation, so we're going to choose the positive root for that equation. So choose the positive one. R is positive 0.5913. Use a regression calculator to find the correlation coefficient R. What does this value tell us? All right. So this is a positive correlation. It's not very strong. Remember what we're looking for. A correlation coefficient of 1 would be perfect, like 100%. All right, this is only like a 59% match, kind of. All right, I guess that's, I don't know. It's not a very strong correlation. It is a positive correlation. It's just pretty weak. Use a regression calculator to find the p-value. What does this value tell us? All right, well, we've got these numbers over here. And did they give us the p-value? Yeah, right here. P-value, 0.2937. 0.2937. So we can see p equals 0.2937. What does this value tell us? You got to go back to when I talked about p-value. Remember how we wanted it less than 5%? If it was less than 5%, then there's a that supports a conclusion that there's a linear correlation between the two variables. So this is not a very good result. It's not what we want. Okay, this would say not enough evidence to conclude there is a linear correlation. Remember earlier when I was talking about stuff that happens by chance? Okay. Those dots could have just been there by random chance. It's not, we don't have enough evidence to conclude that there's actually this linear correlation. All right, now, example 4 is the exact same example. We're still talking about shoe print and height, but this time it bumps it up to 40 dots instead of 5 dots. Okay, 40 dots instead of 5 dots, and that looks a lot better. It's a way more obvious that these dots are going uphill. Okay, it seems a lot less obvious, or it seems like it would not be by chance. If I wanted to come over here to 35, I could guess there's going to be a point, you know, in here somewhere, right? I've got a pretty good idea of what's happening there. Well, here are the numbers for you. Here's the correlation. R equals 0.813. That's pretty close to 1, right? So that's pretty good. And the p-value is 0.00. So we've got a pretty strong, or at least stronger, correlation. And with this, we can conclude, because it's less than 5%, we can conclude a linear correlation. And if we can do that, then we can find the equation of the line. So I told you, you know, down here at the bottom was an equation. You know, we've got an equation of a line right here. It doesn't really make sense to give me that equation if there's no correlation, if you can't tell if there's a correlation. But now, when we've got this evidence to show that we can say that there's this linear relation, this linear correlation, we can come up with an equation. That equation looks like, well, what was it? 1.7x plus 125, right there. 1.727x plus 125. that would be the actual equation of the best fit line through those dots. That's basically what regression is. Regression is finding that equation. Excuse me. Given a collection of paired sample data, the regression line, or line of best fit, or least squares line, is the straight line that best fits the scatter plot of the data. The regression equation has the form, now this is going to be weird, y hat is how you would say that, y hat equals b0 plus b1x. That's really weird. I think it's going to be weird to you to put it in that form, because I mean basically that's the same thing as y equals mx plus b. It's just written in a different way. But this book prefers to write it in this form. So if you see it written in that form, don't freak out. It's just the same thing as slope-intercept form. It's written backwards though. They must have given us the y-intercept first, and then the slope and the x second. It's the same thing, so don't freak out when you see it written that way. Number 5, regression line. Use the data for latitude versus the number of skin cancer deaths, mortality, for the 48 contiguous states and DC. To find a regression line and the correlation coefficient, either enter the data manually or copy paste using this file from the QR. Okay. So I'm not sure if that QR code works well. It's hard to copy and paste. I had a little bit of a difficult time with that, but that QR is supposed to take you to this file. I also posted this file on my Schoology page. So this file, it's basically talking about skin cancer deaths versus latitude. And if you think about it, would you expect more skin cancer deaths in the north or in the south? In the south. Why? Closer to the equator, more sun, and stuff like that. So is that what this seems to say? You know, find a southern state like Florida. I don't know. Delaware's pretty high. Connecticut's low. Colorado's pretty low. California's pretty high, I guess. What's the biggest number on here? Texas is pretty high. Tennessee is pretty. It seems like the hotter southern states are generally going to have more mortality. But anyway, if you go to here, you can copy this and paste this into the linear regression calculator, which I've already done. Okay, I already did that. And so does that seem to be a positive correlation or a negative correlation? That appears to be a negative correlation. Or as x increases, y decreases. As the latitude increases, the skin cancer deaths decrease. Or as we go north, the skin cancer deaths decrease. That's what that says. What do we have to do? Come up with the equation and the correlation coefficient. So the equation is easier. That's down there at the bottom. Okay, I'm going to write it in the backwards form that they give me. All right, this is mx plus b. I'm just going to flip it around and write it backwards. We'll talk more about y in a later lesson. But we've got y equals 389.2 minus 5.978x. And the correlation coefficient, they don't give it to me quite. They give me this r squared value, 0.6798. R squared is 0.6798. So r squared equals 0.6798. You have to understand that when you square root both sides, there's a plus or minus root. Which one do we want? We want the minus because it's a negative correlation. We can see on the graph that it appears to be a negative correlation. So we use the negative one. Square root of 0.6798, we're going to get an R value of negative 0.8245. Negative 0.8245. All right. Now, there's at least one or two questions on the homework that I did not cover, so I need to actually add something in there. So there's space at the end of your notes. So I'm going to add another question here. Example 6. This is the last one, though, I promise. Talks about critical values. This is another thing that'll be new to you. And we're not going to get into how to find critical values as much as how to use them once they're given. All right. So a lot of words. Use correlation coefficient R equals 0.591 and critical values R equals plus or minus 0.878 to determine if there's sufficient evidence to conclude there is a linear correlation. All right. So here's the way I look at it. The smallest value R could take would possibly be -1. That would be if there was a perfect match, perfect negative correlation. And the highest it could possibly be is +1. And in the middle there is 0. Those are the only numbers in between -1 and 1. That's all there is. All right. So we're going to graph the critical points. The critical points are going to be about right here. That's 0.878. And about right here, that's negative 0.878. So got a lot of words here, but basically what you want is anything inside this range right here is going to be considered close to 0. And so not a good correlation. Anything outside that is going to be considered close to 1 or close to -1, and so therefore would be a good correlation. So really all we have to do is say, well, 0.591 is right here. And since that's inside, we're going to say that's close to 0. Numbers between the critical values are considered close to 0. So what can we say? We don't want it to be close to 0. There is not enough evidence. To show a linear correlation. critical values does the same job as the p-value. I would rather do the p-value because that calculator, that regression calculator, just shows me the p-value. Look for a p-value that's less than 5%, 5% or less. That's good. That does the same job as this. Critical values, we don't really know how to find them yet. Maybe we'll find those later, but for now, they're going to give you critical values and that correlation coefficient, and you do this. If it's inside that range, we're calling it close to 0, so no evidence. If it's outside that range, we're going to call it close to 1, and so that would be enough evidence.